Hi, this is Philip Cassidy, and this is my Lab 3 circuits for Physics 2. And a quick introduction, some of the purposes and ideas were to predict behavior of circuits, show how resistors and capacitors work, and to use voltmeters and ammeters. The models we'll kind of go through as we do the experiment, well, the simulation, as we'll see. But this was one of the first ones we did on the right, with the two batteries, two resistors, and the two ammeters. And some of the principles we used were energy conservation, current conservation, and charge conservation. And those all apply because of the closed loop rule. And two of the equations we used were Ohm's law, where V equals IR. And then also the equation to the right, delta V equals delta V naught times E to the negative T over RC. And these were some of the results I got. And I'll get into them after we go through it. But for the assumptions, a system and initial conditions, because this was a simulation, the simulation assumes there's no resistance in the wire, ammeter, or voltmeter. And this gives us a very ideal case, which is not typically seen in an actual experiment. But for the system, we have the circuit where the surroundings are everything else. And the initial conditions are that there are no ammeter or voltmeters attached to the circuit. This doesn't really matter. But I just want to include it for completeness. The experiment and results for part one. This is where we had to determine the resistance in different parts of the circuit. The current I got from Ohm's law was 0.02 amps, which was also what we saw in the simulation, which is a good sign that things were going right. And then if the current flowed in the opposite direction, I was expecting the ammeter to read negative, but there were only positive values that I saw. And I'm assuming this is the simulation just trying to keep all the numbers positive. But then when the loop is not closed, both the ammeter and voltmeter read 0, which makes sense because it's not a closed circuit, so there's not going to be current flowing through. And those were some of the voltage readings I got. You could kind of see that in the graph at the bottom. And we have decreases from C to D when it goes through the resistor, and then an even steeper one for the 100 ohm resistor from E to F. And everything else does not change the delta V. And the sum of the potential differences should be 0, and that is the answer that's given in the circuit. And that makes sense because it is a closed circuit. And more results, the ammeter and voltmeter are both acting ideally in the simulation. In reality, this wouldn't be the case, and some of these numbers would change. And when we added the second ammeter in series, the ammeter acts as a resistor in parallel, and you can see this on the right. And this changes the current in both the ammeters. So instead of the 0.02 number we see, it goes to 0.06. And again, these are the same numbers for the resistance, 48 ohms, 102 ohms. And then because this is ideal, it's 0 ohms in both the wire and the ammeter. And now for part two, this is when we included the capacitor, both charging and discharging. As the capacitor charges, the bulb gets dimmer over time until it completely goes out. And when the capacitor discharges, the bulb also gets dimmer over time until it goes out. In both scenarios, the current decreased over time. And the 100 microfarad capacitor took 6 seconds to charge and then discharge, where the 200 microfarad capacitor took double the time, 12 seconds to charge and then discharge. And for the slope of the graph that we did to calculate the RC value, which is the time constant, it was negative 0.1675. And that's from the graph over here. And the RC value you get from that is 5.97 seconds, which is almost exactly what we expected to see, where the 200 microfarads times the 30 ohms is 6 seconds. And the data versus model and sources of error, there were very minor errors in this lab because it was simulations rather than human experiments. And since we're in the ideal setting, there's much less room for error. If we were performing this in the real world, there would be much more error. And we could see this just from the ammeter and voltmeter because they would not behave ideally. And the only real human source of error in this lab was stopping the timer at the exact time to get the exact readings from the voltmeter, which then changed the graph that I got the slope for. And the what if questions, a real ammeter has some resistance included within it. This would have affected the lab because it adds an extra resistor to the circuit, and this would change the readings of the ammeter. And if there was no resistor in the circuit, the capacitor would charge in 0 seconds. And that's from this equation. And if there's no resistance, you get 0. And in real life, the answer would be a little longer because there is some resistance in the system through the wire.